Hello, dear students. I'm here trying to record a second lecture, basically targeting for our task 2. So relating about multi-objectives and penalty function and trade-off. So as the first lecture, I have already provided, so this will be basically a, let's say, a appetizer or a kind of supporting material just to facilitate your self-learning experience during this week and during your task solving or before your task solving. All right. So the learning objectives for actually this week or for task 2 basically are the 3 following. So the 3 levels. First, on knowledge and understanding, it's clear if you read the book already, it is about penalty functions and also graphic representation of trade-off methods. So these 2 keywords are very clearly illustrated in the task and also in the book. And on the skill and ability level, we would like to be able to select let's say materials in a systematic manner, when especially the design objectives are having a conflicting situation. And lastly, towards the value attitudes, we would like to let you realize there's always the compromise we have to make during the selection of engineering materials or during the design. And actually, if you just go even broader level, compromise actually is everywhere in our life. And we're basically making selection, making decisions, and making compromises every day in our daily life. So in addition to the chapters in the textbook, I could also draw your attention in the following 2 additional books and also their related chapters. So if you're interested in it, feel free to visit and have a look at them. So the outline for this small, let's say, exercise or lecture here is basically the following 4 chapters. So first, I'm going to give you a little bit theory background or sort of strategy when we just deal with 2+ objectives and why they're conflicting and what is our kind of strategy to deal with it. And then I'm going to detailed explain you what are the trade-off methods we're going to use. So the concepts we're going to use. And then I will show you some details in this trade-off methods. Basically, it's about the penalty function and there's exchange constants. And finally, I show you a few examples. So hopefully with these examples, you can really sense this concept, the strategy, and the details of the lecture this week better. But before we move into, let's say, the main concept of this week, I would like just to recap you with what we have learned from last week. So I think the most important knowledge or concepts were quite nicely summarized in this graph. So we're dealing with actually going from design and towards the selection of materials. So if you just remember, we started with the design requirements, right? And we try to first let's say the 4 steps when you come to the selection of engineering materials. The first step is we try to translate the design requirements into constraints and objectives. I hope you still remember everything about this. And on the other hand, we have the data. So the data is about the material attributes and process attributes and so on. So these are available in the software and in your knowledge base. And basically, we then try to marry both of them. Then we go to the second step. Basically, it's screening, which is related to mostly the constraints. And then we go to ranking, which is usually related to objectives. when we want to do a certain optimization as cheap as possible, as light as possible, for example. And finally, we do a documentation through graphs or through just listing, and then you get your final selection of your material. So those 4 important steps, yeah, it's a really a high level concept. I hope everybody could still have a quite sense about it. And now we're gonna move to the reality. So last week you learned how to build up a single objective, especially towards the math. So we always want to minimize the math to fulfilling a certain, let's say, certain level of force, certain level of deformation in a way. But in a reality, actually, they either constraints or objectives could be both multiple. Yeah, the constraints actually are already multiple. Maybe you didn't notice from last week. We are actually listing constraints, multiple constraints, and they're just not functioning for one of them. Actually, they're all functioning at the same time. You didn't realize it because to just sort out these materials that don't fulfill those certain constraints is rather easy, right? You just narrow down to your material database, and then you can leave the materials that fulfill all the multiple constraints. The difficult part is on this multiple objectives. Yeah, we are dealing with a optimization process. Even for one of the objectives, we're optimizing already. But when we have 2, let's say, objectives, we need to do, let's say, 2 optimization processes. If they go hand in hand, they're optimizing to the same direction, that's everybody's happy. Yeah. But actually, in the reality, most of the cases, they don't go hand in hand, they're just conflicting with each other. And here I'm giving you 2 most commonly seen minimization or optimizations of 2 objectives. Yeah, the first is mass. We know this already pretty well from last week, but the other is cost. Yeah, so last week, everybody in the exercise session, a flipped classroom session, I think, let's go with the CFRP, right? Carbon fiber. That's the best. That gives the best, the lightest and the highest beams bending stiffness. That gives the lightest and also the highest tension strength and so on. Yes, everything is true. But why don't you see for all the engineering products we're using carbon fiber? Yeah, because they're rather expensive. Yeah, and so today we're gonna go closer to the reality, and when we just apply both of them together, so as light as possible and as cheap as possible, how should we do? I'm here giving you let's say, a very simple example that probably everybody has faced in your life at a certain point, when you want to buy a bike, something like this. Yeah. You will actually already feel this kind of conflicts. Yeah. Here it's a very simple example, because we don't think about any, let's say, strength level requirements, bending stiffness, nothing. You just take the bikes in the market and you just plot their price against their weight in such a simple diagram. So don't look at the trade-off surface and everything. Just look at all these dots. Yeah, you will see the bikes, in the market. They will go in such a shape rather. Yeah. So you will find very, let's say, expensive ones, and at the same times, they're also pretty light. If you want to go the low price, so rather cheap ones, they will automatically become rather heavier. This is just a nature outcome. And this actually just displays you, yeah, about this kind of conflicts between multiple objectives. Here I'm trying to give you, let's say, a conceptual level theory about multiple objectives and the optimization for these multiple objectives. And basically, the method we're going to use is the so-called trade-off method. Yeah, it's just like when you make a choice, you make a compromises. You always need to go with a trade-off solution. So first, like I try to get you familiar with the certain terms. Of course, you can find all of this in the book. So I'm going to go rather bravely. If you don't follow here, don't mind. Again, just reading the book. I just try to here give you a swift overview about the concepts and tasks and some details. Just let's look at the same diagram. So steel mass and cost. And first, we are listing basically here materials. So each bubble here is representing one material. In our sense, is one solution. Means this material or this solution actually could fulfill already those constraints. You have already finished your screen and you plot all the, let's say, the remaining candidates in this diagram. But naturally you will see the candidates here, they have two different groups. So we kind of call them, the first group is so-called dominated solution, and the other is so-called non-dominated solution. What is the difference between those two? So you can see the non-dominant solution means they are actually optimal, in a certain sense. Because here we cannot find the overall optimal, because the best one is right here at this corner, because our convention is to minimize things. This is a little bit different from the concept we were having last week. When we were doing the material index, if you remember, the capital M, we always try to optimize because we're going to this corner, and that's always easier to find out, because otherwise we have to go to this corner and maybe inactive. That's something we don't like. But this week, just for the convenience use, we're gonna go with again with this corner. So we try to minimize things. So this is something you need to pay attention. I will emphasize this again when we come to the later example. But here, just remember, we're trying to do the minimization. But all of those non-dominated solutions, they're not providing a overall minimization. They're not overall minimal. They're kind of, let's say, local minimal. If you look at this guy, so this guy is probably the cheapest, right, compared to the other ones. When they're also having a same mass. So if we have a constant mass, we know we're gonna buy this, because this one the cheapest. The same if you just go the other direction. This is also the lightest one, right? If you just go to the same price, if you have a budget limit, if you want to buy a bike, okay, this is my limit. Let's say you're gonna find this one, because all the others are heavier than this guy. And so this is one of them, and all of this have a similar feature about this. So this leaves us the difficulty how to choose. So this is the trade-off. Basically is the optimization is basically fulfilling a kind of banana diagram, and this is very typical in many engineering problems. And so it's kind of banana shape. And we therefore call this this shape on this front or this surface, if you have it in a 3D plot, you have mass, cost, maybe CO2 footprint or something like that, you would formulate a surface, which is called trade-off surface. If we have a 2D plot, we will call it the trade-off curve, or you can also call it parietal front. Basically, they're the collection of, let's say, the non-dominated solutions or the so-called local minimums. All right, I hope everybody now gets the concept about multi-objective optimization and what is the trade-off front or trade-off surface when we have multi-objective situations here. Yeah, so you basically don't have a solution that you say, okay, that's my best. So you have to choose from many, let's say, possible best ones. Then the question is, how do we do the selection? Now we have to make a selection after all. Yeah, I mean, the easiest way, I already just simply mentioned a little bit already in the last slides. Yeah, if you still remember the bike example, yeah, you have cost and mass. You say, I have a budget limit, yeah, certain money right here, and then you see, okay, within this budget, I choose the lightest one. Yeah. Or you have, let's say, a strength limit. I cannot take the bike heavier than what? Then I also draw a horizontal line. I would take the mass only like that. Then I choose the cheapest one. Yeah. But in most cases, you don't have such a very clear strength goals. Yeah, because you're rather flexible. Yeah, things are flexible, and that's why we try to use a rather flexible method, which is called the penalty function. So you see, we want to minimize two variables, cost and mass, at the same time. Yeah, basically, then you just what is the easiest way to combine two variables, and you make a linear function of them. So then you just use a linear function. This is z is your penalty function, and then you just use c plus alpha times m. Yeah, this is a very simple linear function, and alpha is basically a scaling parameter or weight parameter. It has a certain value actually, or certain meaning in many cases. I will explain also slightly later. You will find this in a book for many cases. Yeah. So this is our solution. Yeah. So this is the simplest, but I think it's also very practical solution. This penalty function. Of course, you can also formulate other penalty functions. Yeah. This is the, let's say, simplest and also practical one. You can also formulate a, let's say, a power law. Maybe you formulate a second order function. Yeah, everything is possible. Yeah. So we're going with this. Yeah, basically the task is becoming, we find a solution with the smallest z. Yeah. So this helps. Yeah. Why? Because now you are not just looking something from one curve. You will easily formulate to draw another curve, which is this linear shape curve, z. I think I don't need to explain how this will be plotted. Yeah, this is some mathematics we need to recall maybe from high school or so. Yeah, because we're having the y-axis as m, so mass, and the x-axis as c, cost. So we have to revert everything. The slope will be not alpha here, because this is the y-axis is m. Yeah. So the slope is -1 over alpha. So the intersect is basically 1 over alpha times z. So basically we're looking for the minimal intercept, and this is also this curve, right? And when you find this intersection here, basically this is your optimal solution. You're minimizing the z, and this is the trade-off front you can find. Yeah, I hope this is clear. So basically, to find your desired, let's say, selection of the material, you formulate a trade-off function to help you find your guy from this trade-off front or trade-off surface. All right. Now let's try to use this concept into a few examples. That's quite easy to understand the concept. Actually, you will see it's not that easy to apply, because we still need to make many decisions. Yeah. First, let's look at this example about this bike. Let's say you now still listed all this existing bikes in the market, and you see now you can kind of draw this trade-off surface exactly looking like this. Yeah. Another banner shape. Now, instead of using horizontal or vertical line, which is rather rigid, and now you can think about, okay, yeah, I'm flexible with my budget a little bit, and I'm also flexible with my strength. But I think my strength is worth a certain amount of money. Yeah. Let's say if you are value more about your money and your value less about your strength, you think, okay, I can go with $20 per kilo. Yeah, and then this is basically your penalty function. And then you can easily find a best candidate, yeah, somewhere here, with, let's say, with steel. And if you just go with, okay, you say, oh, I want to save my strength. I don't want to exercise too much by the bike. I want to rather exercise with the cross trainer. Yeah, and you can give a $2,000 per kilo, and then you could add up with something like, let's say, at least aluminum alloys or titanium alloys. Here's what about titanium alloys, or something close to that. Now, as you can see, this is really something helping you, yeah, quantitatively to select your best candidates. But this is very individual, and this example is just to give you a sense of this whole concept, how it could work in your even daily life. You can find actually other cases that could work better. Yeah. But this concept works actually pretty well when we just talk about engineering systems, because in that sense, the alpha, this kind of value has a more, let's say, physical meaning. Here I'm giving an example about the material for transport system. Yeah, why it has a physical meaning? Because here the cost is also having a little bit more sense. I mean, mass is something simple, but in the transportation system, you can actually reflect your mass in terms of fuel, because your fuel consumption will be directly correlated with your mass. Yeah. And the cost is just not the initial cost when you just buy your material. Yeah. Actually, it is also the cost plus the lifetime. Yeah. If you think about the cars, you're going to basically refill it every week or every few days. And those fuels will be directly contributing to your cost. So the cost will be initial cost plus, let's say, the lifetime cost, which is kind of correlated with M. So in this sense, you can see our penalty function, this kind of linear shape, very simple one, right? Z is equal to C plus alpha M, is making perfect sense, that it combines this field inside very nicely. And here, this alpha has a physical meaning. It is also called an exchange constant because it represents the money you spend per each kilo. You can very much correlate it to fuel kind of consumption, and finally to the price of your fuels, either, let's say, gas or benzene or diesel and so on. Yeah. So here I'm giving you a few examples of this alpha. You can see they will make really good sense because for cars, let's say, simple, let's say, passenger cars, this alpha is typically ranging from 3 to 6 euros per kilo. Just to give you an idea, these are really rough number. Yeah, we're talking about a whole car. So you know that the car has so many different materials. We're just talking about, let's say, the major consumption, the major component of the car. I mean, because you will see other examples, we will give you even more detailed alpha ratios later. But here we're just giving you an overall, let's say, figure about this alpha in a system level. Yeah. So be careful with this. This is a system level thing, cannot be very, very specific. Yeah. But you can understand when we just talk about the cars and the passenger vehicles, let's say this alpha is about 3 to 6 euros per kilo. And that's why you see we're using a lot of steels in the passenger vehicles. Yeah. Because your simple small vehicle is usually about 1 ton and 1.5 ton and so on. And around about 60 to 70% of that mass is contributed by steel. Yeah. So that is the reason. The reason for why we're using steel is because this alpha ratio is relatively small. But when we go with the heavy trucks, you will see it is a combination between steel and aluminum, because this alpha ratio is becoming larger. As you can imagine, this kind of, especially its truck components, they're usually produced by aluminum. And when we just go further and further, you can see commercial airplanes, military airplanes, and finally rockets or space shuttle. Actually, we're going to more and more expensive materials. So here you see CFRP composites heavily used here before, let's say, before SpaceX came. I will explain that later, maybe in the flip classroom. Because here the alpha ratio is becoming much more expensive. You can imagine if we just drive something in the ground, you can correlate your fuel consumption. Let's say that's something minor, or not minor, but something not that significant. If you just push some mass into the space, with the 10,000 kilometers away or so, this will be extremely expensive. You need tons of fuels, and you can imagine this alpha ratio is becoming really high. So we want to save any mass we want to have over there. All right, this is the second example. Lastly, I want to give you the third example, which is already related to, let's say, our task in a way. And it is also becoming more engineering, because the other two examples are rather conceptual and more related to let's say, daily life. Here it's really about the design of a certain component, and things are also becoming a little bit more complicated. Yeah, because a simple illustration you can already see, you cannot just use M and C directly. First, let me introduce what is this example. So here we are trying to, let's say, select a material for the front bumpers for a passenger automotive. Yeah, the front bumper, I think everybody knows, is this thing. Yeah, this horizontal beam right here. It will use to basically absorb energy when you have a crash, most likely low speed crash in the city. And this will really save your life, because it will just absorb energy and deform and make sure you don't get really heavy kind of acceleration or deceleration of your neck, and also make sure the space of the drivers or also the passenger will not be deformed heavily. That could injure you. All right, so as you can see, it is a problem about bending strength. Yeah, so here you should be careful, because the load will come and in a bending mode, but you need to think about why it is bending strength, not bending stiffness anymore. We talked about a lot about bending stiffness last week, So think about why we are talking about bending strength here. And so for the bending strength, we have this let's say as light as possible and as high as possible for the bending strength. I think you are familiar with this material index. Yeah. So the complication here is we cannot use mass and cost directly. Actually, we have to use mass per unit bending strength and the cost per unit bending strength. Now, this is the difference between this one with the other examples. Because here we have to think about the bending strength. Yeah, we cannot just use mass and cost directly. That's why we formulated with the material index concept, if you still remember. But pay attention here, the material index is formulated differently. So it's not because in the material index for, let's say, as light as possible and as high bending strength or stiffness possible, we actually usually put the sigma yield 2/3 or 1/3 into the numerator. But here, we're not in the numerator, but in the denominator. Maybe you still remember the thing I emphasized at the very beginning. For the material index, single objective, we're looking for the, let's say, highest M. So that's why we try to formulate according to the maximum. But here we're looking for the minimum. That's why we just revert it. And the density comes to the numerator and the strength comes in the denominator. So this is something you need to pay attention to and understand why we're doing that. And the same thing is for the costs. But actually the cost is something very easy to understand. It is just kind of proportional to the M right here. This is also something you can easily imagine. But what should be paid attention, it is also formulated to unit bending strength. So here, the penalty function is not simple anymore. It's a little bit more complicated because we're going to formulate everything with, let's say, this mass per unit bending strength and cost per unit bending strength. So this is the additional term, but inside you can see it's still about this Cm plus alpha. All right, so that was the concept. Now I'm going to show you how do we visualize it. How do you do the, let's say, ranking and do the selection. So the first way to rank it or to visualize it is by the bar charts. Basically, you just plot all the materials possible that all fulfill the constraints, and you just gave the y-axis as your penalty function. This is exactly what we have plotted according to the equation before, and alpha is 100 euros per kilo. And you can see if you just list it as we're looking for the minimal, and here you can find the RP is the best one. And okay. And if you want to just make it the plot a little bit more vivid, or in the providing a little bit more information, we would like to teach you how to use the bubble chart to do this penalty function. Here we need to do a little bit difference, or we need to pay attention a little bit to this bubble chart. I'm going to show you right away. Because we're not just plotting M and C, and we're actually plotting this M1 and M2. So M2 is related to weight, and this is the roll over sigma y, and the M1 is related to cost. This is the Cm times roll over sigma y. So you need to pay attention to this. And as you can see, we can still construct our trade-off surface looking exactly like this. And these are all the, let's say, local minimums. And now it's a question, or it's a task to visualize our penalty function. So this is how our penalty function will look like if we formulate with respect to M1 and M2. Yeah, so this is the difference if you want to plot it with a bubble chart. Yeah, you have to give those parts into your each cost and mass. Yeah, and this how it looks like. You see, it's although it's a linear function, but it's becoming nonlinear. And the reason is simply we're using log scale. I remember, yeah, that's the scale we're still using. And you can see here is how it looks like when alpha is 1. So when alpha is very small, so €1 per kilo. Then you will go, let's say, with the selection of what? Low alloy steels and carbon steels. That is good enough. Yeah, if you go with the alpha as 10, then you will find aluminum alloys, magnesium alloys are the very good solutions. If you go with alpha 100, and you will find carbon fiber and reinforced composites are your best selections. Yeah. So basically, this is all of it. You can see alpha makes a decisive role. Yeah, in our course, we're not going to ask you to derive the alpha. Actually, to derive alpha is also a very complicated issue. You can easily imagine this alpha is really involved not just, let's say, the benefits of the car maker, the companies or their principles. It could be also correlated with the whole political view and the environmental protection, right? And so it could be a complicated issue to do. So basically, the alpha will be given, and what you should be what you need to should pick up is basically when you just have those alphas, how would you like to formulate it, and how you could use this penalty function to assist your selection of engineering materials.